Kevin, team, are you ready?
Yes.
Yeah, okay. Is everyone ready? Okay, good morning, good afternoon, good evening, our colleagues. Welcome to the World Large River and Delta System Source to Sink webinar series. Today it's my pleasure to introduce our speaker, Dr. Tim Dellapenna from Texas A&M University at Galveston. So before I give a detailed introduction about Tim's work, let's move to the next slide, Paul. And I want to talk about the webinar series. So we have a YouTube channel. If you search Source to Sink, you should be able to find our channel on YouTube. You can follow us. In addition to that, we also have a Twitter account. Paul, if you, yeah, okay. So the Twitter account is also called Source to Sink, and you can follow us on that. And if you have a Twitter account, you can receive lots of notifications about the announcement of the talks and webinars. Next slide, please. Okay, a quick heads up for next week. So next week, we will have a special seminar. It's co-organized by multiple universities as well as CSDMS. So we will have the speaker Jaya Savitsky from Community Surface Dynamics Modeling System. We will have a new time. Okay, I want to emphasize we will have a new time. It will be the Eastern noon time on Wednesday, December 1st. Let me repeat. We will have a different time. It will be noon time, US Eastern time on Wednesday, December 1st. So that will be the Western time, 9 a.m. So I hope lots of colleagues along the West Coast of the United States can join us. And then it will be London time, 5 p.m., Paris time, 6 p.m. I believe it's probably around midnight, Beijing time. So I apologize for our colleagues from Asia. So Dr. Savitsky will be giving a talk about Anthropocene impact, about the Earth's sediment cycle during the Anthropocene. So it's a very exciting topic. I think he will give us a global view about the sediment cycles during a pretty recent period, geologically, in the Anthropocene period, which is normally since 1950. Okay, next slide, please. Okay, so Dr. Tim Dellapenna now is associate professor in the Marine and Environmental Science Department at Texas A&M University at Galveston in Texas. So he was assistant professor, and then before that he was a postdoc at Texas Institute of Oceanography. So Tim received a BS in geology from Michigan State, two MS degree. One is geology, the other is hydrogeology, both from Western Michigan University. Tim received a PhD from Virginia Institute of Marine Science, WIMS. So he probably left WIMS around 1999, and I joined WIMS in 2002. So we did not overlap the WIMS, but I have heard lots of great research done by Tim. So Paul, I think you probably overlapped with Tim maybe for a year or two.
Yes, we did.
Okay, great. Yeah. So so Tim's research is mainly based on combined usage of short-lived radionuclide geochronology, sediment analysis, high-resolution marine geophysics to investigate the record of modern sedimentary processes in estuarine and nearshore environment. And in particularly, his research is focused on the natural responses to anthropogenic alternation within the Anthropocene. So in fact, today, Tim's talk is also highly relevant to lots of human activities. which is a good one, which is a good transition to next week's talk done by to be given by Dr. Swisky. So that's it. So now I would like to give the floor to Dr. Dellapenna.
Great. Thank you very much, Kevin and Paul. It's a real pleasure to speak to this group. I'm going to jump right into it. I want to first give a shout out to Guanhong Lee, who's joined us as an audience. I should have had him as a co-author because much of what I'm going to talk about in Korea, all of what I'm going to talk about in Korea, I did through him and with him. We're going to look at two different contrasting stories here. We're going to look at the impact of Hurricane Harvey in Galveston Bay and how anthropogenic alterations within the bay set the stage for the impacts that we saw. And this is in stark contrast to the estuaries in Korea, where we're looking at how the alteration of the estuary through the installation of estuarine dams, seawalls, and land reclamation have altered the system and resulted in significant natural feedbacks as well. The picture on the left is a...
Tim, you haven't shared the screen yet.
Oh, my. Thank you. How's that?
Good.
Okay.
Looks good. Thank you.
Thank you. Sorry. The picture on the left is a plan of something that in Texas is called the Ike Dike, which is something being proposed where they're going to put, if they do it, they're going to put large floodgates across the mouth of Galveston Bay, do large seawalls and some level of land reclamation, which would alter the bay system in a comparable way to what we probably have seen in Korea. So I'm going to just go to the next slide. So first question, when I give this for a more general audience, I go through this, which is why are estuaries important? Well, as marine geologists, we probably have a pretty good idea of this, but I'll go through this. They provide a buffer between the rivers and the ocean. They filter nutrients, contaminants, and organic matter. And when we say filter, what we mean is they accumulate these materials in the sediment, as well as to some extent in the biomass, so that it doesn't enter the ocean. It's not that they leave the system, but that they get trapped within the estuary. Estuaries provide a nursery ground and habitat for finfish and shellfish and other marine organisms. And it provides both a commercial and recreation fishery and navigable waterways, ports, and harbors, which in all of the estuaries that we're going to talk about, those are significant factors. Estuaries are threatened by both urban development, which include nutrient and contaminant loading, excessive sediment loading, elevated land subsidence due to fluid withdrawal, and also reduction in sediment and fluvial inflow in some cases, loss of space due to land reclamation, and a removal of the estuary by portions of the estuary by the installation of estuarine dams and tidal barrages. In this study, we'll focus on the physical changes to an estuary and a natural feedback due to loss of surface area due to land reclamation and estuarine dams, as well as changes in accommodation space due to land subsidence and the associated impacts that causes. So to begin with, a couple definitions. When we talk about accommodation space, it's the space created for new sediment to accumulate due to a relative sea level rise. This can be created by eustatic sea level rise or by land subsidence. When we talk about estuaries versus deltas, we see this picture actually John Anderson put together a few years ago, or his folks, and it shows an extremely exaggerated version of the Texas coast with Galveston Bay shown on the right, with which occupies the incised valley, Trinity River and San Jacinto valleys, and then the Brazos Valley on the left, which is actually completely filled. And the difference between these two systems is simply sediment supply. So an estuary is forms, our coastal plain estuaries in Texas form on incised valleys that haven't been completely filled by sediment. And so for an estuary to be maintained over time, or let's say the Holocene, sediment accumulation needs to be equal to the amount of accommodation space created. That is to say, it's filling at a rate less than the accommodation space that's created by sea level rise or land subsidence. Whereas the case of the Brazos, the sedimentation rate exceeded the sea level rise rate, so it filled. So it's no longer an estuary. Another term we're going to talk about is a tidal prism. And it's simply the volume of water that flows in and out of an estuary during a tidal cycle. And then there's a relationship between tidal prism volume and tidal inlet cross-sectional area. The bigger the tidal prism, the bigger the cross-sectional area. And through analysis of a number of estuaries that plot generally along this relationship, if they're natural inlets, we see that this relationship is pretty well established. So if the tidal prism increases and the inlet is not engineered, it's a natural inlet, then it'll expand. If the tidal prism decreases, then the tidal inlet tends to decrease as well. So alterations in the tidal prism will lead to specific feedbacks to the estuary. We can also talk about along coastal plain estuaries, we really have two end members. We have the tide-dominated estuary, which tends to be funnel-shaped with bars that are parallel to the direction of the flow. And the sources of energy is primarily due to the tidal energy. These typically are found in meso to macrotidal estuaries, but can exist in some cases in microtidal estuaries where the wave energy is very low. Example would be Delaware Bay. A wave-dominated estuary is typical of having a mouth bar across it, barrier of some sort, barrier island, barrier spit. It's perpendicular to the direction of wave energy. Wave energy is greater than tidal energy, and these typically are found in micro to mesotidal estuaries, such as Galveston Bay. Now, the key factor is it's the dominance of energy. It isn't just the tidal range. You can have microtidal, tide-dominated estuaries, and you can have at least meso to macrotidal, wave-dominated estuaries. An example of that would be the Copper River estuary in Alaska, which is almost macrotidal, but still has a mouth bar across it because wave energy is so strong there in the winter. Another point about tidal prism is that if land reclamation occurs, then we're actually reduced the tidal prism by reducing the available space for the tidal prism. So this is what this figure shows is land reclamation will cause there to be less volume for the water to flow in, so it'll effectively reduce the tidal prism. If you reduce the tidal prism, then you're reducing the tidal energy that can move sediment around. So you're going to end up with, if all things are equal, increased sedimentation in these conditions. Shout out to Natalie Scheider, one of Guan Hong's PhD student. I borrowed this from her work that's in prep. So here's a photo of, give an example, land reclamation in Incheon Bay in Korea, 1984. We see that there's some land reclamation, but it's relatively limited compared to what we see in 2021. In fact, the large feature in the middle is a man-made island that is where the international airport is. We see the area over here. I believe this is Songdo, which is completely reclaimed in the last 20 years, and Estuarine Dam down here where they've actually closed off an estuary. And again, land reclamation in this area and building out of urban space. Here we see I'm not going to attempt to pronounce the name of this place, but it's in China. And we see in 1984, this is an area that has been recently reclaimed. And when we jump down to 2021, this is the area that had been claimed in 1984, and this is new area that's being reclaimed today. The same with this urban center right here was under reclamation in 84. So we see dramatic loss in the estuarine space through land reclamation. And this is the Sammengong sea dike, which was installed as the largest sea dike in the world. bigger than the one in the Netherlands. And they turned this entire estuary into a freshwater lake. Then they turned it back into an estuary again. And you see extensive land reclamation along the banks here, dramatic loss in estuarine space. And then there's another estuarine dam up here, the Coombe River estuary. And this is one of our study sites I'm not going to discuss today, that has, again, extensive alterations because of the installation of this dam in the early 1990s. So this is actually from work that I've been doing with Dr. Lee, and started this in the early, I think 2011. And this was Josh Williams' PhD dissertation. We looked at the habitat alterations, geometric and geomorphic response to estuarine dams and land reclamation in South Korea. And this is an estuarine dam. And we'll see a couple other examples. There's another one. So estuarine dams and estuarine barrages, they are a dam placed within the tidal portion of the river to control flow of water, to extract hydroelectric or tidal power, and impound fresh water, and also in some cases block the saltwater wedge from moving upstream, and for flood control, or a combination of all of the above. Here's some examples of some estuarine dams in Korea: the Ansan system, Nakdong, the Sea Dike. I'm not sure. Well, here's the dam down here in this system, the Coombe, and I'm not going to attempt to pronounce this one as well. But here, again, the estuarine dam goes across the mouth of the estuary. In some cases, they're somewhere within the tidal portion of the estuary. This dam actually went in 1930. Even systems that don't have estuarine dams in Korea, especially on the western coast and the southern coast, have still been heavily modified. So we see extensive land reclamation, seawalls in this system, and land reclamation in these areas as well. In total, 49% of the estuaries in Korea have been closed with estuarine dams or tidal barrages. Most of the estuaries on the western or the macro tidal coast have been closed, many of them on the southern coast, only a few on the eastern coast. And that's because this is a rocky microtidal system, and the estuaries are very small. They're more or less just small mountainous river mouths. So there isn't much estuary to close over on this side. But as I said, the dominant area where they're closed are on the western coast, although we see abundant ones in the southern coast. In fact, look at the rivers in Korea. The largest river is the Han, and it does not have a dam on it. But then we go down to Nakdong and Coombe, and they're both closed. And so the three of the largest of the four largest estuaries in Korea have been closed. The five estuaries in Korea have been closed with estuarine dams. So overall, we look at the size of the watershed. The largest watersheds, 71% have been closed, and the smaller watersheds, only 37% have been closed. We're going to talk today about the Yongsan estuary in Mokpo and the Nakdong estuary near Busan. So one with a tidal range of 4 meters and one with a tidal range of approximately 1 meter. We've worked on Coombe, but we're not going to present that today. That's an even higher tidal range. The Nakdong system, the first dam went in during Japanese occupation in 1930, the Naksan Dam. And it was completely silted up. I believe they've removed the dam in the last couple of years, but when we did this study, the dam had not been opened in 70 years, 80 years, I guess. The Nakdong dams were installed on this side in 1990. The Western Dam only opens during high discharge events, and the Eastern Dam is opened on a regular basis. In fact, one of the floodgates is always open, and these dams open from the bottom, so the bed load can escape. And so this is a core coverage that we did, a couple of seismic lines that we collected that we're not going to show. Paper we got out was Josh. So we see a map from 1927. We see one kind of oddly shaped island. One could argue that might be a barrier island, but mostly it's a funnel-shaped estuary. And in 2012, we have barrier islands across the mouth of the estuary. All of the gray area shows land reclamation. So big areas of the estuary have been reclaimed. And so as you see, the system's been heavily modified. So our research vessels that we used local fishing boats. In some cases, we had to aid the vibrochords in the tidal flat areas. And what we found was that this core, particularly core 19, really told the story for us. What we see is around 19 pre-Naksan Dam installation. It was a sand-dominated system, more closely resembling a delta. Then it got closed and it became a mud-dominated system afterwards. And when we put this together, what we found was these are sedimentation rates. Our lowest sedimentation rate was found in the Naksan portion, which was the first one to close, and our highest sedimentation rates are found in the areas that are more actively open and closed. And a point I would like to make is that in this area, relative sea level rise is approximately the same as global. So we're talking about 2.5 millimeters per year, but we're seeing nearly an order of magnitude higher sedimentation rate. So these aren't even the low sedimentation rate of 1.5 centimeters per year is really a high sedimentation rate for an estuary. And what we see are three different kinds of estuaries. We have the West Nak Dong here. That is, here's the dam here, and it's a mud-filled basin with a barrier island at the mouth. Very comparable to a bar-built or a wave-dominated estuary. And then we have an estuary down here that has sand throughout much of the estuary. So much sediment is coming in that they continually have to dredge it to keep it open, so we couldn't get any cores in this area. But much more resembles almost a tide-dominated estuary in that there's a lot more sand in the system. And this is kind of an intermediate between the two. And what we're seeing here is, again, a bayhead delta that's forming now seaward of the estuarine dam because it does receive some sediment when the dam is open. So here we pretty much see the bayhead delta merging right on top of the mouth bar. So when we look at the original 1927 version, it was pretty much the geometry of a tide-dominated estuary. We look at the 2012 version of the system, it now resembles a wave-dominated estuary. I misspoke when I said that this resembles a tide-dominated. What I meant to say was the bayhead delta has merged with the mouth bar. It really is still, with this mouth bar here, a wave-dominated system. So we've seen estuary change from one type to another because of these anthropogenic alterations. And if you think about it in terms of the impact on the ecosystem, not only do you have these really high sedimentation rates, but on top of that, you're changing the substrate. That's going to have a massive impact on the benthos, for instance, and you interrupt the benthic pelagic coupling, and that cascades through the ecosystem. And it probably caused a near collapse of some of the fisheries in this area. Sedimentation rates after the dam went in increased 10 to 30 times pre-alteration rates. The estuary converted to a wave-dominated system and is actively filling and converting to a delta and prograding seaward. At the current rate, the entire system will be converted to a delta, and all estuarine habitats and ecosystems will be completely lost within 100 years. And this is for the Nak Tong. We'll talk about the Yongsan estuary. This system is a bit different because it's a deeper water system to begin with. Tidal range, so the drainage basin is 3,500 square kilometers. The river length is 140 kilometers. The tidal range is 4.5 meters. Wave height is suppressed, and the dam went in 1980, creating Yongsan Lake. And everything above the dam, of course, that was the tidal exchange was completely eliminated. So here's the dam here. And this, having been an estuary, is now a freshwater lake. And this little section right here is the new estuary. The dam eliminated 98 square kilometers, or about 65% of the tidal range, intertidal area. We see the gray areas here are areas that were reclaimed, and then the red are seawalls that were installed, and then here's the dam right here. So 17 square kilometers of intertidal zone was reclaimed by the dam. Below the dam, and there was a total of 80 square kilometers of intertidal zone. So 17 kilometers here, a total of 80 kilometers for everything we're showing here that's in gray was eliminated. Used a slightly larger version of the Nakdong vessel. Again, we've got nice paper out of this in 2014 with Josh. And in this case, because the water was deeper, we had 10 meters plus in most cases, we had to use a gravity core. And what we found was that, again, sedimentation rates throughout the system increased dramatically. So again, this is more of a RIA than a coastal plain estuary. It's a rocky shoreline. And again, relative sea level is approximately the same as global sea level rise. So we're talking 2 to 3 millimeters per year, and we'd expect sedimentation rates to be comparable. Instead, we're seeing sedimentation rates in excess of 10 centimeters per year below the dam. And even above the dam, we had sedimentation rates of a centimeter or 2. So it wasn't that it was low compared to below the dam, but it was still elevated compared to what it was before the dam went in. And so this area down here is where we saw the most dramatic change in the highest sedimentation rate. So what we reached the conclusion is that the anthropogenic alteration of the Yongsan estuary greatly modified the sediment transport dynamics. Some of the papers we have out of this discuss how it changed the timing and the intensity of the discharge, and it also shifted the depositional environments within the system. Land reclamation eliminated large areas of the intertidal zone and reduced the area where sediment could be deposited. Sediment accumulation rates, again, increased by 1 to 2 orders of magnitude. And as with the other system, high accumulation rates have dramatically impacted the benthic system, community, and overall ecosystem health, although we don't have any data to back that up in our study. So on the story of estuarine dams, it's an ongoing story, but what we've reached the conclusion so far is that estuarine dams reduce the overall tidal prism, increase sediment trapping efficiency, resulting in orders of magnitude increase of sedimentation, both within the estuary and the proximal shelf, and redistribute sedimentary environments in benthic habitat, and likely dramatically impact or cause the destruction of the benthic ecosystem. So one of the points that we talk about, James Savitsky is going to talk next week, most likely, or Jaya Savitsky is going to talk about the export of sediment during the Anthropocene. And here we're showing where these alterations have happened. We're actually seeing the trapping of sediment, coastal sediment, rather than the export of them in these systems. Now we're going to really shift gears, and we're going to talk about Texas, specifically Galveston Bay, and the impact of Hurricane Harvey on Galveston Bay. And I'm just speculating back in 2017, this time in 2017, I was actually out frantically conducting this study. We've worked both on the Brazos Delta. I actually was out on an NSF funded cruise that put me at the mouth of the Brazos during its historic peak discharge. And that's a different story for another day, but here's the mouth of the Brazos down here. We're going to focus on Galveston Bay up here. And this is a beautiful MODIS image showing the sediment plume coming out of Galveston Bay. Although the larger drainage basin is the Trinity River, as you'll see, the San Jacinto River is actually, that's how we pronounce it in Texas, where more of the sediment was coming because that's where the bigger flooding happened. So let's step a little bit away from the hurricane and just set the stage for what was going on before the storm. Houston was a city that was built on oil. Big oil discovery in about 1900 was the Spindletop field just east of Houston. And then shortly after that, we had the Goose Creek field that was discovered up here. And in fact, the first refinery was installed right along here. Humble Oil, which is now ExxonMobil, largest refinery in the world, is located right in this area. And to support all of this refining activity, they pumped groundwater. They pumped a lot of groundwater. They pumped so much groundwater that in about 50 years, the land subsided 3 meters. And so this is a great example of what happens with elevated sea level rise. In that we have a dramatic relative sea level rise of up to 3 meters in the past century in this area. Since then, they've stopped the groundwater withdrawal and ceased the subsidence. The subsidence is still there. Interesting thing is the executives at Humble Oil had houses on the bay, and those houses are now out in the middle of the bay in some areas because of the subsidence was so great. So yeah, this is the population of Houston, and I'm sorry, this is annual groundwater pumping, and this is showing the population of Houston over time in different areas: Galveston County, Fort Bend County, Harris County, right here, which is where the bulk of Houston is. And around I'll go through this. Following the opening of the Houston Ship Channel in 1915, large water was being consumed for the refineries, but it really took off beginning of World War II, and that's where we see this big jump right here. And then we shifted in 1954, like Houston went in and we started shifting towards surface water. But it wasn't until 1976, 77 that we completely eliminated the use of, or largely eliminated the use of groundwater and shifted over towards the surface water with a couple of reservoirs. And so we see that the groundwater pumping has dropped off since then, although it's still used for agricultural purposes. So I had my PhD student, Muhammad El-Mukami, asked the question, did sedimentation keep pace with subsidence? And this was done in the early 2011, 2010, 2012 area. And so we did a series of cores up here, and we used radioisotopes to determine sedimentation rate. And we found that the sedimentation rate is highest up in these areas where the subsidence was highest. And that makes perfect sense. But actually, what we found was the sedimentation rate didn't keep pace with subsidence. It was actually about half the rate of the subsidence rate. So sedimentation is extremely high, 2 centimeters plus per year up here, but subsidence was on the order of 4 centimeters per year. So these areas of the bay have actually gotten deeper. And I'm just showing the incised valley of the Trinity and the San Jacinto River system right here. But we see the highest sedimentation rates are up in here. Another thing that he did in this study was he looked at mercury and its accumulation within the base sediment. So we had this beautiful data set already before Harvey hit that showed the sedimentation rates and also analyzed the mercury content within the base sediment. So one point is mercury is largely a point source. It actually comes primarily from one facility, Oxyvinyl, which is Occidental Refinery in this area on a little tiny bayou. We call our bays or sloughs bayous here for some reason. And I'll show you a picture of it, but it's all pretty much coming from this facility right here. And this is a core that we collected, core 22, which really tells the story in the system. And so this is looking at our pre-Hurricane Harvey mercury concentrations within the bay. We see mercury as high as 162 nanograms or micrograms per kilogram. And this is area, so this is the Buffalo Bayou, flows through Houston through this, and then the San Jacinto flows down here. You got to have special permission to come up here. And we didn't have that when we did the study, so we didn't take any cores, unfortunately, up in Patrick Bayou or Buffalo Bayou. We'll talk about that in a little bit. But what we see is that the source of mercury is over here, and the highest concentration of mercury in the bay system is up here. Our background mercury concentrations are on the order of 20 to 30 micrograms per kilogram or nanograms per gram. And we see over in the hinter areas of the distal areas of the bay that mercury concentrations are near or at background levels. But up within Trinity Bay, and this is a little side estuary called Clear Lake, where there's refineries and other potential sources of mercury, agricultural sources as well. We have higher concentrations as well. So mercury concentrations, average in the San Jacinto River, 150 nanograms per gram. Throughout the rest of the bay, it's more on the order of 20 to 50 nanograms per gram. So this is actually Patrick Bayou, and this little discharge site is actually the source of the mercury. Just going to zoom out a little bit. So this is a little slough right here. You can't get under this bridge right here. It's about a half a meter above the water, but I got in here and got a core a couple years ago. So this is Buffalo Bayou. It flows through urban Houston, and this is what's called the Houston Ship Channel area. Turning Basin is somewhere over here, but this is the heart of the refinery and industrial Houston right here. This is also the Port of Houston. This is actually the ExxonMobil refinery complex over. It's pretty massive, and there's more refinery over here as well. Yeah, that's it right there, because that's Scott Bay. And so this is Galveston Bay down here. And again, this is Patrick Bayou, and this is Morgan Point right here, which is marks the separation from the San Jacinto estuary and Galveston Bay. As I mentioned, I got this one core in Patrick Bayou. We measured mercury in this core. This is the X-ray of the core. This is a photo of the core. Nice core. This is actually the Hurricane Harvey layer right here within the core. 18 centimeters of Harvey mud. And we see in this core is 51,270 nanograms per gram of mercury. So this is 1,000 times higher than background. It's among the highest mercury concentrations we found anywhere in an estuary. I believe I saw Kuwait Bay had a 70,000, and Penobscot Bay was on the order of 50, 60,000. So these are extremely high mercury concentrations collected right here, just downstream of this outfall. And even below that, we still have concentrations of 10,000 nanograms per gram. So we're still dramatically higher than anywhere else in the bay, way above background level. And so we looked at, actually got a couple papers out last year on this, looking at the impact in the San Jacinto as well as Galveston Bay. And so let's talk about Harvey a little bit. So Harvey was our big flood. It resulted in, it made landfall down the coast in Corpus and actually Rockport, moved inland, and then moved inland across urban Houston. In fact, I evacuated to, sorry, I keep on moving my screen here. I evacuated to College Station with my family, and then the storm started coming towards us. So we drove back through the storm back down to where I live in Lake City. And I got to experience this dramatic rainfall. It was, it produced 3.6 times the entire volume of the bay flowed through the bay from Harvey. And the flood lasted for 44 days. We had a total of about 54 centimeters of rain in about 3 days. It was crazy. And then in some portions of the bay, the flood lasted for 44 days. So actually here is a little more to the story. This is, I lost my cursor here, but the circle shows the USGS station, and then these two orange features way off on the west are the Barker and Addicks reservoirs. These are surface water retention areas that aren't actually reservoirs in your classic sense. They have dams, but they're dry most of the time. In fact, there's some neighborhoods that were developed inside of the reservoir. They went in 1948 and largely forgotten about by the developers. And there's golf courses and riding trails and sports fields, except when there's a flood, then it's all underwater. And so the San Jacinto, the North Fork, we show up in the top, the blue, this is an area where there were no dams. And so it was a 7-day flood for this portion, as well as the Trinity River. But because these reservoirs were here and they were starting to fill, the Army Corps of Engineers did a slow release over 50 days. So we flooded everything downstream, lots of lawsuits going on, the whole area downstream, the homes too close to the bayou got flooded. This is Buffalo Bayou. It flows diagonally all the way across urban Houston and through across the mouth of Patrick Bayou and into the San Jacinto estuary. So again, Buffalo Bayou here, 53-day flood. The other systems, 7-day flood. Here's a simulation that Jabi Du and Keong Park put together using their schism model, showing the Harvey flood. And this is looking at salinity. You'll note that the salt wedge actually got pushed out of the mouth of the bay in this case. First time I've ever seen that done here. So what we see is that during the flood, we had, during the initial phase of the flood, we had the Trinity River flooding for about 7 days and pushing water out of the bay. But then we had the slow release of the Barker and Addicks Reservoir that had a prolonged but lower intensity flood that trapped fresh water in the bay for over a month and increased the residence time within the bay. And the models that Javi Du's put together for Galveston Bay has found that a trapping of the fresh water primarily within Trinity Bay and a little bit within East Bay, and that will help explain some of the distribution of sediment that we see. And we had extensive scouring of the bay bottom, estuarine bottom along the lower Buffalo Bayou and the San Jacinto and the estuary as well, which we'll talk about in a few minutes. So I went out with my trusty boat, the RV Lithos, and actually had NPR, National Public Radio reporter out the first day we went coring, did a nice little story on this study. And we did some vibrocoring. This is a submersible vibrocore. We also use a more traditional Aztec land-based vibrocore off this boat. And we collected a series of push cores. Now, most of our data is from these push cores. This is a benthos check valve attached to a polycarbonate tube and attached to a long pole. And we just shove it in the bottom and pull it out. And you can actually see the Harvey layer right here in this core. And we shot x-rays of the cores. And we looked at the sediment content, the mercury content within the Harvey layer within these cores across the entire bay. This was unfunded. I just said, okay, here's a great opportunity. Let me get out there and see what we can find. So this is core 22, which we collected in 2012. So this is part one of Muhammad's cores before Harvey. This is from Scott Bay, which is actually right where the ExxonMobil refinery complex is. And we see is that we have a nice peak of mercury at about 2,000 nanograms per gram. Actually, yeah. And we can match that up to our post-Harvey core. And this is the peak right here as well. And that's where the comparisons kind of break down. This is our post-Harvey core. And by having the X-radiograph and the previous in the post-core, we can actually see this is a Harvey deposit right here. This is a scour surface from Harvey. This is bedload deposit with actually some articulated and disarticulated bivalves, sandy, gravelly, shell gravel that is, dominated layer and mud above it for a 22 centimeter deposit overall. And because we had this pre-Harvey core, we actually can see now that we lost 48 centimeters. So Harvey scoured or eroded almost a half a meter of high mercury content sediment, and then deposited a lower mercury content sediment above it. So a dramatic scouring in this area due to Harvey. So we lost enriched mercury sediment, and then it eroded down during Harvey, and then we deposited a new sediment pile, which still has high mercury content, but much lower than it did the stuff that was scoured. And so when we look at all of this data together, we see that 131 million tons of sediment were deposited in Galveston Bay from Harvey. And so that's 25 years of average sediment load in a course of 2 months were brought into the bay. Most of this was probably brought in the first week of the bay. And then the sediment was trapped within the San Jacinto area where we had the high subsidence rates, and also up in Trinity Bay. And this feature right here is called the Texas City Dike. It extends from the mainland all the way out here. I'm going to use freedom units. Actually, yeah, it's about a 15-kilometer long dike that was put in 1915 to keep this harbor trap open here, and it was very effective in trapping the sediment up here as well. And these other features are oyster reefs. Somebody needs to mute. And these are all the cores we collected from Harvey. So we compared the pre-Harvey mercury to the post-Harvey mercury. The maps don't show much difference if you just compare the two, but we actually compare and we subtract one from the other. We actually see that mercury was enriched both up here as well as out in Trinity Bay, and to some extent even up over in East Galveston Bay. And so in conclusion on Harvey, what we see is that we had actually, I'm going to go up for a couple slides here. I talked about, yes. So I had these out of order. So when we had the Harvey event, we had initial flooding of both the San Jacinto and Trinity rivers, and it flushed water out of the bay pretty rapidly. But then we had the prolonged flooding because of the Barker and Attic reservoirs that slowly released water, and those waters got trapped within Trinity Bay and within East Bay. And so I show you the higher mercury content in these areas, and that's because these mercury-laden, the sediment that was mercury-laden was trapped up in these areas for up to 2 months. Another thing that we found, we haven't talked here, is that this, all this fresh water in the bay actually caused a dramatic kill off of the oysters in the bay as well. We had some of the big reefs actually had 100% mortality. So I want to point out that in the early 2000s, Galveston Bay represented over 10% of the US wild catch of oysters. So it's a pretty significant system for oysters in the United States. And Hurricane Ike wiped out the oysters, and then 10 years later, Hurricane Harvey did the same thing again. Now they're back in recovery. So Harvey delivered 132 million metric tons of sediment, 25 years of average sediment load. It also scoured 4 tons of sediment from Buffalo Bayou and about 1 ton of sediment from the San Jacinto River, and it delivered, we identified 5 tons of sediment of mercury, I should say, not sediment, so 4 tons of mercury from the Buffalo Bayou, 1 ton of mercury from the San Jacinto, and we trapped 5 tons of mercury in Galveston Bay. We don't know how much mercury was exported from the bay out into the Gulf of Mexico during the flooding, but what we do know is what we found within the bay. And it appears that nearly all of the mercury came from that Buffalo Bayou site. So the elevated subsidence, what it did was it created the accommodation space that allowed for the sediment to accumulate. We talk about estuary being a filter. Well, what we really mean is the estuary traps the contaminants. And so in this area, the San Jacinto estuary, where we saw the dramatic increase in subsidence and sedimentation rate in the last 100 years, we also saw that that's where the mercury was trapped and accumulated. The flooding, so this mercury there was in a time bomb, a legacy time bomb that when the flooding happened, scoured, as we mentioned, 1/2 meter of sediment was scoured from up in this area. We don't know how much was scoured in Buffalo Bayou specifically, but the scouring of the sediment then was able to release that mercury and just distribute it across the bay. And as you can see, much of this was actually thrown right at where we have our estuaries as well. And so in conclusion on my entire story, when we look at anthropogenic impacts, they're different for different types of systems, but they're significant across the board. We see that land reclamation, estuarine dams within Asia, specifically Korea is the example we talked about. They reduced the tidal prism, and by reducing the tidal prism, we decreased the energy that can scour sediment, and so we end up trapping sediment within downriver of these dams with a 10-fold increase in sedimentation rate, which then consequently impacts the ecosystem, requires more dredging, and also creates a situation where we have we can deposit legacy contaminants that so we create legacy contaminant inventories within the estuaries that are potential time bombs if we have storms that then redistribute the sediment, comparable to what we saw in Galveston Bay. Within systems where we have elevated subsidence, we also are increasing accommodation space. As a result, we increase sedimentation, we create legacy contaminants that are also potential time bombs that can be redistributed. So one aspect is that where you have high sedimentation rates within estuaries, you're also accumulating the associated nutrients, organic matter, and contaminants, and they're available for redistribution when the system gets disturbed. The other thing I haven't mentioned here is these high sedimentation rates must be having a huge impact on the benthos systems, the entire bay ecosystems, because you cannot have benthic organisms surviving these kinds of sedimentation rates. And if you wipe out the benthos, then you wipe out a big portion of the food chain. And that's what I had today. Thank you very much.
Thank you, Tim. Excellent talk.
Thank you.
Okay, now we open the floor, and if you have any questions, you can either type your question in the chat box, or you can unmute yourself and ask the question.
Hi, Tim.
Hey, Guan Hong.
Hi, it's great talk.
Thanks.
You talked about estuaries being a sink of sediment, but many of the researchers talking about estuary being a kind of a pathway, so that most of the sediments are delivered to the ocean, right?
Yes.
And do you have any assessment how many percentage of estuaries are actually trapping sediment compared to delivering sediment to the estuary?
Well, for an estuary to be maintained as an estuary over time, the sedimentation rate needs to be balanced with subsidence, sea level rise, or accommodation space formation. So for these estuaries that are stable, that haven't been dramatically altered, then they're really bypass systems. But then we look at the systems like in Korea, they're no longer bypass systems because we've modified them. And now we're archiving, we're collecting sediment. The systems are getting transformed from estuaries to deltas because we're trapping, we're more or less, as I said in the Nakdong example, we're creating the Bayhead Delta seaward of the dam. And so we're filling the system in. And so in those cases, and I believe, I didn't throw the slide out, but I believe Natalie came up with 25% of the estuaries in the world have dams in them now. So 25% of the systems are being converted from estuaries to deltas. That's a way of thinking about it that we really haven't talked about before. So in areas where we have enhanced subsidence, such as river deltas like the Mississippi Delta, it's sinking. So we're accumulating sediment within the estuary as well as transporting it offshore. So in areas where we have high relative sea level rise or an estuarine dam, we're trapping it. The rest of the systems we're probably bypassing.
So would it be fairly, safe to say that if we altered system, the estuary system, human alter system by building dams or then subsidence, and then the natural course of estuary, discharging sediment to the ocean will be altered, and then instead of discharging it trapping sediment.
Yes, absolutely. That's very fair to say. And the reason largely with the dams is you've removed much of the tidal prism, so you no longer have the ability to flush the sediment out of the system, as you well know, because your graduate students have demonstrated that. Yes.
All right.
Very good
Thanks.
point. That when we talk about river deltas, these are our new river deltas. Small, they're not the big ones, but we're literally converting estuaries into deltas by converting the estuary.
Any other questions?
Hey, Tim,
Yes.
fantastic talk.
Thank you. I
This
appreciate
is
it.
a very, very cool work for particularly the impact of the Hurricane Harvey to this estuary and the Bay Area. So my question is, because there's so much sediment dumping here, more than 100, 130 million. So did you have a calculation with this kind of event every couple of years? So do you think how many years the bay will be filled?
Well, this was, depending on whose numbers you look at, a once in 500 year or once in 500,000 year event, which we probably we'll see. Those numbers mean nothing really. Yeah. But as we see a increase in these kinds of events, we're definitely. That's a good question. How many of these events would it take to fill Galveston Bay? Is really what you're asking. I haven't made that calculation. It's an interesting idea. It's something we can do, and I think it's worth doing. Just having, I would say, maybe 100 of these would completely fill the bay.
So followed about that, you show in some place the sediment accumulate up to 40 centimeters, right?
Yes.
So did any evidence show after the event, after a couple months, or after winter season? So is the sediment still there, or maybe reduced to 20 or 10 centimeters?
Well, it's interesting you asked that, because the samples we collected at the Texas City Dike, which is where the sedimentation was highest within the open bay, we actually collected those samples 9 months after the storm. So we collected them in May. The storm happened in September, and that's what was left after the storm. I have an ongoing project I've been doing this semester, funded by the Army Corps of Engineers, where we're actually resampling all of the Harvey sites. And that's the assessment we're doing right now, is to see how much, because we get 30 cold fronts a year. So that's what, almost 150 cold fronts blow through the system since the storm. There's going to be a lot of sediment redistribution.
Wow. That's cool. Very, very fantastic. We need to do this in our Palmico Sound in North Carolina. We haven't done this work. That's beautiful. So last question. So you showed so much up to tons of mercury coming down. How about the water column? Is the water column, maybe Keon or other colleague, they maybe monitor water column, the mercury concentration?
Well, mercury is particle reactive. It does not stay in a dissolved phase at all. So the only time that we have mercury in the water column is when there's a sediment.
Suspension.
Yeah. And I showed these data to Texas Parks and Wildlife, or Texas Environmental Quality folks. And they actually said the mercury levels weren't high enough for them. They didn't feel that it was going to have an impact on oysters.
So the oyster mainly killed by the sediment, not really the mercury, or maybe combined.
Say that again?
The oyster. You said oyster,
Oysters are suspension feeders. So they're feeding on a suspended sediment. But the concentrations, by the time they made it to the reef, they were, twice what they'd been before. And plus all the oysters got killed off during the event. And so the new oysters that are coming up, they certainly are living in an environment where there's higher mercury within the bay, but probably not high enough to create action levels.
I see. Wow.
But still, fortunately for you and me, mercury is bioaccumulated. And so we have enough winters behind us to probably not have to worry about it, but our kids probably don't want to feed them oysters.
Okay, wonderful. That's fantastic. Okay.
Great. Thank you, Paul. This has been a fantastic series. I appreciate this.
Any other questions?
Cool.
Okay, thank you so much.
you.
Thank you for your
Bye.
participation. Special thanks to Tim. Yeah,
Thank you.
it's a wonderful talk.
Yeah.
Good night, Wan Hong.
Well, this is
Right.
Thanksgiving time, and everyone who ever have a Thanksgiving.
Great. Thank you,
Yeah.
Paul. Goodbye.
Okay.
Okay.
Thank you, Kevin.